In this video, we're going to take a look at solving rational inequalities. This would be like having a rational equation, but with an inequality in place of the equal sign. They're solved actually much differently than rational equations. So if you struggled in that section, don't panic. This one is quite different. And actually, I kind of think they're a little bit fun. Let's take a look at solving rational inequalities. In the first problem that we have from this section, we've got x minus 7 divided by x plus 6 greater than or equal to 0. When we're looking at this, we're trying to figure out what values of x would make this fraction either equal to 0 or greater than 0. When we're looking at this, what we're going to do is divide up the domain according to the values that give us the vertical asymptotes and the values of the x-intercepts. In other words, the places where it intersects or crosses the x-axis, or the places where it cannot touch or cross the x-axis. To do that, we're going to look at the denominator of each equation and set it equal to 0 and solve to get the vertical asymptotes. Then we'll set each numerator equal to 0 and solve to get the x-intercepts. Then we'll divide up the real number line according to those values, and we'll take test points to plug the test points into the fraction to see whether or not the value is greater than or equal to 0. The fact is, it can only change the sign of the graph at one of these places, either at a vertical asymptote or at an x-intercept. Otherwise, it has to stay on the same side of the x-axis. Let's take a look at what we mean. We're going to go ahead and solve this one, and then I'll graph it in Desmos and talk more about what solving these is actually doing. First, we start by setting x plus 6 equal to 0 in order to find the vertical asymptotes. Remember, vertical asymptotes are the places where the line cannot be touched or crossed. The graph has to skim along the sides of it. In this case, by subtracting 6 from both sides of the expression in the denominator, we get x equal -6. Vertical asymptotes are the zeros of the denominator that do not cancel. We'll also look for holes if we have holes. Zeros of the denominator are places where the domain gets split apart. Now we want to look for the x-intercepts, which is where the numerator is equal to 0. We take the x minus 7 and we set it equal to 0. When we solve this, we get the x-intercept, the place where it crosses the axis, as 7. In other words, when the numerator is 0 and the denominator is not 0, we know that the y value is 0. This is the ordered pair 7, 0, indicating that, again, this is a place where the graph could change sign from being above the axis, or positive, or below the axis, or negative. Now we're going to take these values which interrupt the domain, and we're going to put them on a number line. Here's 0 for a reference, -6 to the left and 7 to the right. We're going to divide up the real number line into regions. We have the region here between negative and infinity up to -6. Then we have another region here between -6 up to 7. And finally, we have another region on the other side, which goes from 7 out to infinity. The 0 in this case was not one of the values we found as an x-intercept, a vertical asymptote, or a hole. It's not a 0 of the denominator or a 0 of the numerator. So it does not count to divide up the domain. Let's take our test points. We're going to divide up the number line into regions based on the zeros of the numerator and the zeros of the denominator. The values we found were -6 and 7. 0 is here just as a reference to let us know about where the -6 and 7 should go, but it does not divide up the domain because it was not one of the values we found. Then we take a test point in each region. You'll see that I've color-coded the regions just to distinguish one from another. We're not including the values -6 or the value 7. They're empty. A value that is below -6 would be -7. Any value below -6 would work, but -7 is probably the easiest. Any value between -6 and 7 will also work, but again, 0 or 1 would probably be the easiest to use. For a number that's greater than 7, I chose 8. Now I take those values and I plug them into the original function where I've replaced the variable with an empty set of parentheses. Substituting -7, I get -14 divided by -1, which is +14. What I really care about is not the 14, but the fact that it is positive. That means in this region, the entire graph is above the x-axis because the y values are positive. What about in the next zone, which is shaded pink? In the next zone, I replace the variable x with the 0, my test point, and I get -7 over +6. Again, I don't care about the number so much. I care about the sign. The sign is negative, which tells me that the entire graph in this pink shaded region is below the x-axis. All the y values are negative. Now I take a look at the last region, which is shaded in blue. When I'm looking at this region, I plug in the test point 8 in place of the variable in the original inequality. This gives me a +1 over 14, which is positive again. So I know that in this region, above 7, the graph is entirely above the x-axis. Now let's go back and look at what it originally said. In the original problem, what we're seeing up here is that the fraction must be greater than or equal to 0. Where did or equal 0 come from? That's a 0 of the numerator, which is the 7. That means that we'll make the 7 solid, but if it comes from a vertical asymptote or a hole, we'll definitely make it empty. Now we're looking for regions that are either greater than 0 or positive or equal to 0. The 0 is at 7, but it's positive in this region and in this region. -∞ up to -6, but don't include -6. As well as 7 to infinity. Let's check again and make sure that this meets our expectations. It's positive here and it's 0 at 7. It's not defined at -6, so we can't include it, but it's positive to the left of -6. Now we're going to put our answer into the solution and see what we get. This gives me, from the left, -∞, comma, -6, with a round set of parentheses to leave it out. Union, square bracket to include the 7 where it's 0, comma, infinity. Close with a round parentheses for infinity. When we check our answers, we see that we get the answer correct. Let's take a look at the next problem. In the next problem, we have x minus 5 divided by x minus 4 greater than 0. This is similar to the last problem, but it's got to be greater than 0, not equal to 0. So don't include the 0 of the numerator in your solution. The parentheses will all be round. I'll leave it to you to work on this one on your own, and we'll proceed to the next one. In the next one, we have 4x divided by x minus 7 less than 2. Let's go ahead and take a look at it, because this time, instead of being greater than or less than 0, it is less than 2. Because we have this being less than 2, we need to do some work before we start looking at the zeros of the numerator and the denominator. In other words, what we need to do is move the 2 to the left and get a common denominator so that we have only one fraction on the left side and 0 on the right side. We're starting with 4x over x minus 7 less than 2. We can subtract the 2 from both sides of the equation without unbalancing it. And this is to get 0 on one side. Then we have 4x divided by x minus 7 minus 2 less than 0. We need one fraction, so we're going to get a common denominator. This is a skill that you may or may not have picked up in earlier classes. To do this, it's similar to the last section where we need a lowest common denominator, but we only have one denominator, x minus 7. So that is our lowest common denominator. What we're going to do now is we're going to multiply the 2 by x minus 7 divided by itself so that we can get it in the form with the same denominator. In other words, we need to have a common denominator so that we can subtract them together. I still have less than 0. Here we're multiplying by a form of 1. The form of 1 consists of the lowest common denominator divided by itself. This gives me 4x divided by x minus 7 minus 2 times x minus 7, all divided by x minus 7. Now that the denominators are the same, I can write these as one combined fraction as 4x minus 2 quantity x minus 7, all divided by x minus 7. The next thing I need to do, of course, is simplify the numerator. In order to simplify the numerator, I'm going to distribute the 2 across both terms that follow it in the parentheses. Note it is a negative 2. This gives me 4x minus 2x plus 14, because I have negative 2 times x, or negative 2x, and negative 2 times negative 7, or plus 14. The denominator remains the same as x minus 7, and it's still less than 0. Now I combine the like terms in the numerator to further simplify it. 4x minus 2x gives me 2x, plus 14. And now it is divided by x minus 7. When we look at this fraction, the next thing we want to do, since we have 0 on one side, is find the zeros of the denominator and find the zeros of the numerator. The zeros of the denominator will either be wholes or vertical asymptotes. We do this before we do any cancellation, because if it's ever there, it can never be allowed. This gives us the value x equals 7. This is going to be one of the numbers that divides up the domain, but this is a number that will have to be an empty circle because it is in the denominator and we can't allow division by 0. The numerator would be a 0 of the numerator is going to be the x-intercept. Always be sure to find these values before you've reduced the fraction. We subtract the 14 first to get 2x equal negative 14. Then we divide both sides by 2 to end up with x equal negative 7. These are the two values that divide it up. X equal negative 7 will make it 0, but we don't know yet whether that's included or not unless we refer back to the original, which has less than but not equal to. That makes both the 7 and the negative 7 empty circles when we divide the domain. The negative 7 is to the left and 7 is to the right. If you want to put 0 on as a reference point, you can, but remember, it does not divide the domain. Only the zeros of the denominator and zeros of the numerator do that. Now we're going to divide the region into sections. I have a section that goes below -7. Remember, -7 is not included because it does not equal 0, and 7 is not included because it was a 0 of the denominator. Now we have the region that goes between -7 and 7. We also have a third region, which is going to become from 7 to infinity. Now, when I look at the three regions, I need to find a test point in each region. I need something to the left or smaller than -7. -8 seems like a good option. I like to circle them so I know which one to use. Between -7 and 7, there are infinitely many numbers, but 0 is the easiest, followed by 1. Above 7, I can again use 8. Now, when I try my test point, I want to try my test point on this fraction here, which is not exactly the original, but is the one where it was isolated and had 0 on the other side. So I'm going to use 2x plus 14 over x minus 7. When I replace the x with an empty set of parentheses, I get this relationship right here. Then I plug each of the test points in turn into this relationship. In the first one, I have 2 times -8 plus 14, all divided by -8 minus 7. The -8 times 2 gives me a -16 plus 14, and -8 minus 7 is -15. This gives me -2 over -15, which is a +2 over 15. What I care about is that it's positive. Then I do the same thing for the 0 test point. Plugging in the 0 test point, I have 2 times 0 plus 14 divided by 0 minus 7. This gives me 0 plus 14 divided by -7, or 14 divided by -7, which is a -2. This means the entire graph between -7 and 7 is entirely below the x-axis, and all the y values are negative. When I'm looking at the next graph, or the next region, I use the test point 8. This time I have 2 times 8 plus 14 divided by 8 minus 7. 2 times 8 gives me 16, and 16 plus 14 will give me 30. In the denominator, 8 minus 7 gives me 1, so I end up with 30. What I care about is that it's positive. Now I want to go back to the relationship where it was isolated with 0 on one side and see what I'm looking for. I'm looking for less than 0, not equal to 0, strictly less than. That means negative. So I'm looking for the region or regions where it's negative. The only region where it's negative is the pink shaded region between -7 and 7. My solution then is the open region from -7 to 7. Let's test our answer. Gotta love the green checks. The next problem is very similar to the ones we've seen before, so I'll let you work on this on your own at home. Remember to first isolate by moving the 4 to the left side and then getting a common denominator, which is x minus 7. This next problem looks a little different, and it's going to have a weird sort of answer. Let's go ahead and look at this one. 4x minus 5 divided by x minus 6 less than equal to -1. That's a little unusual with the negative, but it's okay. It's just a number, and there are numbers that are less than that. This is number 5. We have 4x minus 5 divided by x minus 6 less than or equal to -1. First, we want to isolate and get 0 on one side by adding the 1 to both sides. This gives us the fraction 4x minus 5 divided by x minus 6, the quantity, plus 1 less than equal to 0. Now that we have 0 on one side, we need a common denominator. The common denominator is the only denominator we have, which is x minus 6. I'm going to multiply both sides by x minus 6. This is going to give me x minus 6 divided by itself, which is a form of 1. So we get the LCD by multiplying by a form of 1. Now we can rewrite this as 4x minus 5 over x minus 6 plus x minus 6 over x minus 6 less than equal to 0. Because it's a plus and we have the same denominator, we can go ahead and write them in one combined fraction. 4x minus 5 plus x minus 6, all divided by x minus 6. If this were a subtraction, we would need to put the x minus 6 in parentheses and distribute the negative over both terms in the numerator. Because it's a plus, that's not necessary. Now we combine the like terms in the numerator. We want to simplify the numerator. This gives me 4x plus x, which gives me 5x. The -5 minus 6 gives me -11. Even if it factors and something would cancel, don't do it. Factoring is fine, but canceling is not. We need to know if it was ever there. If it's ever there, then it's either a whole, a vertical asymptote, or an x-intercept. Those are the numbers that divide up the domain. Now we're going to take and look for the zeros of the denominator and zeros of the numerator. We'll start with the denominator. Remember that these are giving you vertical asymptotes or wholes if it cancels. In this case, we add 6 and we get that we have a vertical asymptote, since it does not cancel, of 6. Then we find the 0 of the numerator, which is actually the x-intercept. Because again, it does not cancel. This gives us 5x minus 11 equals 0, or 5x equal 11. Then we can divide both sides by 5 to end up with x equals 11 divided by 5, which is an x-intercept. We use these two values, 6 and 11/5, to divide up the real number line. Think about which of these numbers is larger and which is smaller. 11/5 is close to 10/5, which is 2, so it is smaller than 6. This gives me 11/5 on the left side and 6 on the right. Make sure you get them in number line order, with the smaller to the left and the larger to the right. Now we can divide up the axis into 3 regions. This region, and the last region. Now we want to look at the equation to see if it was or equal to, and to make sure we eliminate the vertical asymptote. It's less than or equal to 0, so it can be an x-intercept, but it cannot be a whole or a vertical asymptote. The vertical asymptote was 6. That means we have an empty circle at the 6. But because it could equal 0, we include the x-intercept, which is 11/5. Now we need a test point in each region. What's an easy number that's less than 11/5? How about 0 or 1 or 2? Pick your favorite. My favorite is 0. What's a number between 11/5 and 6? I know this is close to 2, but I don't think it's 3. Just to be sure, I'm going to go ahead and use 4. What about a number that's greater than 6? How about 7? Now we use the fraction that was in the isolated problem with 0 on one side, 5x minus 11 over x minus 6. When we transform this and replace the 0 with empty parentheses, we get the expression you see here. Then we take each of our test points and we plug it in. 0 plugged into this would give me 5 times 0 minus 11 over 0 minus 6, which gives me negative 11 over negative 6, which is a positive 11 over 6. Now I'm going to test the 4. When I test the 4, I plug it into that equation. 5 times 4 minus 11 divided by 4 minus 6. 5 times 4 is 20, and 20 minus 11 would give me 9. 4 minus 2 is a negative 2. This ended up with a negative number, which means that in this region that's shaded pink, all of the y values are negative, and the entire graph is below the x-axis. Let's do the last region, which is shaded yellow. Using the test point of 7, I have 5 times 7 minus 11 divided by 7 minus 6. 5 times 7 is 35, and 35 minus 11 would be 24. 7 minus 6 is 1, so I get 24, which is positive. Now go back to the original inequality with the 0 isolated. We're looking for something that is less than 0 or negative or equal to 0. We've already included the equal to 0. Now we need less than 0, which is negative. That's the pink region. So it's closed at 11/5 and goes to 6. Our solution will be closed 11/5 up to 6, but not include 6. Let's put this into Desmos and let me show you what it is actually doing. First, I'm going to graph the function, and then I'm going to graph the inequality. Let's take a look at what it looks like when we graph this inequality in Desmos. When we graph the inequality, you'll see that it's actually shading a region. What region is it shading? Well, it's shading the region between 11/5 and 6. It's shading the solution set, in other words, to make this inequality true. Let's move on to a slightly more complicated problem. Well, slightly might be an under exaggeration. And let's see what it does on a more complicated rational function. Let's move on to problem number 7, which is different from any of the problems we've looked at previously. In this problem, you can see that the denominator of this fraction will probably factor. It is certainly quadratic in nature, and probably it factors. Remember that when we were graphing rational functions, we had to factor the denominator and the numerator to see if anything canceled. In this case, when we're looking at this problem, there won't be anything that cancels because the numerator is 5. However, looking at the denominator, it is likely the case that that polynomial, that trinomial, will factor into the product of two binomials. Let's try it. X squared, the middle term tells us, splits as x and x. The last sign is positive, which means the signs in the middle of the binomials are the same. This positive then tells us they're both plus. I need two factors that multiply to give me 27, but when I add them, I get 12. That would be 3 and 9. Notice that this one has already got 0 isolated on the right side. This is sort of a shortcut for us. Now we want to find the zeros of the numerator and zeros of the denominator. We'll start with zeros of the denominator. We'll take the factored form and set it equal to 0. These are zeros of the denominator. They're either going to be vertical asymptotes if they don't cancel with factors in the numerator, or wholes if they do cancel and disappear with factors in the numerator. In this case, we don't have anything that can cancel, so they are vertical asymptotes. Then we use the zero product property that tells us that if two things are multiplied and we get 0, one of them has to be 0. So we have x plus 3 equals 0, or we have x plus 9 equals 0. When we solve that, we end up with -3 for one solution and -9 for the other. These values are the vertical lines that form the vertical asymptotes, and we have 2 of them. What about zeros of the numerator? When we look at the numerator, we have 5. Well, if I set 5 equal to 0, that's false. And what that tells me is there are none. And that means I have only 2 values to divide up the domain. When I write these in the number line order, remember that -9 is further to the left than -3, which is closer to 0. This divides up the number line into 3 sections: below -9, between -9 and 3, and above -3. Again, because these are vertical asymptotes, it cannot equal either one, no matter what the inequality symbol is. We can never allow division by 0. Now we need test points. For a number that is smaller than -9 or to the left, I'm going to test -10. Between -9 and -3, I'm going to test -4. And for a number that is to the right of -3, I'll test 0. Again, there are infinitely many numbers you can check, but you want to use test points that are easy to evaluate. Now we're going to come back up here to the factored form, and we're going to plug in our test points. 5 divided by x plus 3 times x plus 9. This is supposed to be, I believe, less than 0. This leads to 5 divided by some value plus 3, then multiplied by the quantity some value plus 9. When I plug in my test points, I first plug in the -10. This gives me 5 divided by -10 plus 3 multiplied by -10 plus 9. -10 plus 3 is -7. This gives me 5 divided by -7, and -10 plus 9 is -1. This gives me -7 times -1, which is a double negative, resulting in a +7, or 5 divided by 7. That means in this region, it's positive. Do not assume that the one to the left is always positive. That is not the case. It just happens to be the case in the ones I picked to work. Now let's look at this intersection, which has -4 for a test point. Again, we have 5 divided by the quantity -4 plus 3 times the quantity -4 plus 9. When we work this out, we'll end up with 5 in the numerator. -4 plus 3 gives us a -1, and -4 plus 9 gives us 5. This is going to give us the value of 5 divided by -5, which is equal to -1. In this region, the values are all negative or below the axis. Now let's take a look at the next region. In the next region, what we have here is the graph with the test point of 0. When we plug in the test point of 0, we have 0 plus 3 times the quantity 0 plus 9. When we look at this, what do we end up with? When we're doing this one, we end up with the value of 5 in the numerator times 3 plus 9, or times 9, which is 27. That gives me a positive value, which lets me know that this one here is positive. When I enter the inequality, it's going to give me the test solution. I'm going to enter the test solution, but I'm also going to enter in the equation. First, I want to talk about the last problem we did and show you what it would look like if I had put in the equation that corresponded to what we had in the beginning. In the beginning, we had 4x minus 5 divided by x minus 6 less than equal to -1. We moved the 1 over to isolate it. Once we have this isolated, we got a like denominator and combined like terms to get 5x minus 11 over x minus 6. If I were to enter that in as an equation, instead of equal to 0, I put in y equals, I would see what the actual rational function looks like. Oops, I think I probably will need parentheses. 5x minus 11. Ooh, and I put 4. Concern this white keyboard. 5x minus 11 divided by the quantity x minus 6. Now let me stretch this out so you can see what it looks like. I'm going to shrink it down a little bit so we can see this. And I'm also going to collapse the side panel so that we can see it a little better with the solutions that we found from our test points. When we look at our test points, remember that we said below 11/5, it was positive. Note that the rational function, instead of being equal to 0 equal to y, is strictly above the axis when we're on the left side of 11/5. Between 11/5 and 6, it says that the graph is below. Notice that the graph is below here in this region. And in the upper graph, we have from 6 to infinity that the entire graph is above the axis. And here it is entirely above the x-axis. Let's now apply this to the one that we just worked. Our equation is 5 over x squared plus 12x plus 27. That would be 5 divided by the quantity x squared plus 12x plus 27. And this is less than 0, not less than equal to. This time we see the solution set is plotting right here. Let's copy the equation and set it equal to y to see what the actual rational function would look like. Now we can see the actual rational function that corresponds to that particular ratio. When we're looking at it here, let's scroll down to the work we did previously where we have our test points. We use test points of -10, -4, and 0. And we found that the solution to this ended up being, well, where did we put the solution? I guess we didn't put the solution. What were we thinking? What would the solution be? Since this has to be less than 0, it must be negative. And since it must be negative, it must be in this region here between -9 and -3. So our solution will be open -9 to open -3. Look here at the solution, which is shaded in blue between -9 and -3. That corresponds with what we found for the interval. Now look at the graph of the original rational function. Notice that below -9, it is strictly above the x-axis, getting closer, but still above. Between -9 and -3, it is below the x-axis here in the green. And when we're above -3, the graph shown here in green is entirely above the x-axis, showing again that the y values are all positive. I believe the last problem is somewhat similar to the one we did previously, but with 3 fractions instead of 2. Again, you need a common denominator. Why don't you pause the video, set up the problem, then turn the video back on to see if you get what I get. So how'd you do? This was a pretty challenging problem, more difficult than any of the ones we've seen before. Let's take a look at what I did and see if your steps matched mine. The first thing we had here was the rational inequality 1/5 minus 40 over x squared less than equal to 2 over x. First, we subtract the 2 over x on both sides so we can get 0 on the right side by itself. This gives us 1/5 minus 40 over x squared minus 2 over x less than equal to 0. Now we need to get one rational expression on the left side, which unfortunately means we have to get a common denominator for each term. The denominators that we have are x squared, which is x times x, 5 by itself, and x by itself. I've got one column of x's, so I need an x, another column of x's, so an x, and a column with 5. That means my lowest common denominator is 5x squared. What I want to do next is I want to multiply each term here, each fraction, by a form of 1 in what it lacks to be the common denominator in the denominator. In other words, 5 is not 5x squared because it lacks the x squared. So I multiply the 1/5 by x squared over x squared. X squared is not the lowest common denominator because it lacks the 5. So I multiply 40 over x squared by 5 over 5. The -2x has x in the denominator by itself. It's not 5x squared because it's missing one x and the 5. So we multiply it by 5x over 5x so that we can get the common denominator, 5x squared, in each denominator. Don't reduce. If you reduce after you get to this step, you simply go right back to this step and you got to start the process again. Don't reduce. We're getting common denominators so we can combine them together. Since the denominators are identical, we can write one denominator and combine the numerators together. That's x squared minus 200 minus 10x. Once we have it here, notice that the quadratic equation is not in the standard order. It has the constant in the middle instead of the variable term with x. So I'm going to reorder the numerator. The next thing I did when I was looking at this was know that I had to solve for the zeros of the numerator and the denominator. I need them factored to do that. The denominator is a single term, so it's already in factored form. The numerator is a trinomial, which probably factors as the product of two binomials, so I need to factor it. When I factor it, I get x minus 20 and x plus 10. The signs in the middle are different, and the larger product gets the negative. 20x is larger than 10x, so the 20x gets the negative attached, and the 10x gets the positive attached. Now that it's factored, I can go ahead and find the zeros of the numerator and the zeros of the denominator to divide up the domain of the function. When I look for zeros of the denominator, because nothing canceled, I'm looking for vertical asymptotes. Again, we don't actually want to cancel. We need to know where the holes are. It can change sign at a hole as well. In this case, we end up with 5x squared equals 0. Then we divide both sides by 5 to get x squared equals 0, which means, of course, that x is 0. That's a vertical asymptote, so it will be an empty hole when we divide up the domain. Then we find the zeros of the numerator, which is this factored quantity, by setting it equal to 0. We use the zero product property, which says if two factors multiplied together give me 0, one of the factors has to be 0. Solving that, I get 20 and negative 10. Rewriting the problem, you'll see that the next thing I want to do is find out what makes this fraction less than 0 or equal to 0. Remember that the solutions that came from the zeros of the numerator are the ones where it equals 0. That's 20 and negative 10. We're going to divide our number line up by the numbers 0, 20, and negative 10. Negative 10 is furthest to the left, then 0, then 20. The two that were zeros of the numerator, because it could equal 0, become solid dark circles. This divides up our domain into 4 regions: below negative 10, between negative 10 and 0, between 0 and 20, and above 20. Now we want to take a test point in each region. I chose negative 11, negative 1, 1, and 21. This is going to give me 4 different values that I have to substitute into this expression. You'll see here that I apply a little bit of a trick to reduce some of the work that I have to do. When I plugged it in for the first test point, negative 11, I noticed that I had a negative minus 20, which of course is going to stay negative. Instead of tracking the number, I just track the sign of that factor. The second factor, negative 11 plus 10, is also negative. But when I square something in the denominator and multiply by positive 5, it'll always be positive. So that one's a plus. 2 negatives make a positive, and a positive divided by a positive is a positive. So this light blue shaded region is positive. Now let's test the next region using the test point negative 1. Applying the same trick, the first set of factors gives me negative 1. The second factor gives me a positive. So I've got a negative and a positive, which will give me a negative. The denominator will always be positive because it was squared, then multiplied by a positive 5. This gives me a negative, so this region is negative. Let's try the test points 1 and 21. So you can see it, I've reproduced what I'm plugging it into here and written the test points here. When I substitute it in, 1 minus 20 ends up being a negative value, and 1 plus 10 is positive. The denominator, again, is always positive because I square it and multiply by a positive 5. That gives me negative times positive, or negative, divided by positive, which is still negative. Test point 1 is a negative region, even though it's next to a negative region. Test point 21, on the other hand, the first factor, 21 minus 20, gives me a positive value. 21 minus 10 is also positive, and the denominator has been positive from the beginning. This gives me a positive value. Now I look back at the original and remind myself what I'm looking for. Oh yeah, less than 0 or equal to 0. I already have equal to 0 marked here. Now I need less than 0, which is negative. That would be the pink region and the yellow region. But notice it's broken up by the 0, which is an empty circle. So I'm going to start at negative 10 on the far left with a closed bracket, a square one, up to 0 with a round parentheses. Then I need to include the next section, which is yellow, again picking up at 0 with a round parentheses to leave out the hole, going up to 20, including 20 by making that a square bracket. When I test the point, you'll see over here that it is in fact that lovely shade of green. So I know I've done it correctly. Let's put this on Desmos so that we can see what the actual rational function looks like and what the inequality solution also looks like. Let's see how I entered these possibilities into Desmos. To enter the inequality, I put in the one in factored form less than equal to 0. It's what's giving rise to the shaded region that you see here. Notice that we have this solution that is going between negative 10 up to 20. Unfortunately, it doesn't really show the break at 0. It can't show it because it's an infinitely thin line, which means that Desmos is not a perfect way to decide these answers. The best way is to do it algebraically. To find the equation of the line, you replace the 0 with y equals. This is graphed here in the black color. I'm going to scroll in a bit so you can see a little bit more of the graph. The difficulty here is that the dividing line at 0 doesn't show up because it's a single line. When we're looking at this particular graph, we can tell that when we're below negative 10, the graph does go above the axis. You can see it's barely above, creeping up slowly here. When we're between negative 10 and 0, the next region, which is shaded pink, it should be below the axis, and you can see it is below the axis as indicated here. The vertical asymptote is on the line where x is equal to 0, but it does not show up because how can Desmos show us an empty line? Then we have the next region between 0 and 20. Between 0 and 20, again, it's negative, indicating that the graph itself is below the x-axis and the y values are all negative. Then we can see if we scroll further to the right that it does come above the x-axis just slightly once it gets past 20. In other words, the graph from 20 to the right is positive or above the x-axis. I hope this makes sense to you and that you had at least a little bit of fun in finding the solutions to these rational inequalities.